Welcome back to The Explainer. Okay, today we are diving into something truly mind-bending about the machines we use every single day. We're going to embark on a little journey that starts way, way down at the microscopic level of hardware flaws, and we're going to build that all the way back up to absolute digital truth. Seriously, we are tearing down a fundamental illusion about how our machines actually work.
80 to 90%. Let that sink in for a second. When you type a prompt into an AI, it intuitively feels like the machine is doing precise math to give you an answer, right? Well, here is the shocking truth, derived directly from our sources. 80 to 90% of modern AI compute cycles are actually just highly educated hardware guesses. They are not exact math. We are literally building our absolute most advanced digital systems on a foundation of microscopic estimation.
All right, here is our roadmap for today. 1. The grand computational illusion. 2. Shannon's law and distortion. 3. The exact ALU surveyor. 4. The DVR wash cycle. And 5. Scaffolding versus permanent agents.
Section 1. The grand computational illusion.
It's time to pull back the curtain. We love to think of computers as machines that somehow grasp meaning, but physically, they only know resistance and voltage. And this brings us to a really core problem known as FPU mantissa distortion. Deep inside your device, a component called the floating point unit, or FPU, acts kind of like a frantic gambler throwing darts blindfolded. To achieve the absolutely blistering speed required for AI, chip manufacturers literally burn secret proprietary seed tables into the silicon just to approximate answers. They use techniques like the IEEE 754 23rd bit chop, which essentially slices off microscopic fractions of data to save space. It creates this invisible layer of microscopic gunk that makes our entire mathematical tower lean. And this leads to a pretty devastating real-world consequence that's known as the wood chipper effect. Imagine feeding highly sensitive, perfectly exact data into an AI, like, say, a copyrighted book or strict financial records. Because the FPU hardware is approximating the math using those secret seed tables we just talked about, the exact mathematical path of that data is permanently destroyed. It's exactly like tossing fruit into a giant blender. You know exactly what apples and bananas went in, but you absolutely cannot reverse engineer that smoothie back into the original fruits. The chain of title and the data provenance, lost forever. So you might be wondering, is this just bad engineering? Section 2. Shannon's law and distortion. Well, actually, this traces all the way back to Claude Shannon and his foundational work on rate distortion theory. Shannon mathematically proved that anytime you compress or transform a signal in the physical world, you inevitably introduce measurable degradation. It's a fundamental rule. When an AI compresses hundreds of terabytes of data and then generates an output, that algorithmic distortion guarantees that the model's generation inherently possesses a conditional entropy greater than 0. In plain English, it's literally impossible for it to be perfect. It simply cannot perfectly map back to your input. And it turns out, this challenge isn't new at all. It's just evolved. As the sources point out, quote, every single bit transmitted over noisy, unreliable telegraph and telephone lines cost precious money and time. Think about those early telegraph operators relying on copper wire repeaters to battle physical signal degradation over massive distances. Today's modern systems are fighting the exact same battle, just against continuous mathematical noise packed inside a microchip. Section 3. The exact ALU surveyor. So, we have a pretty stark contrast here. On one side, we have the FPU gambler. Yes, it's incredibly fast, but it's lossy. It's completely unauditable, and it relies heavily on probabilistic guesswork. But right next to it, sitting inside our computers this entire time, is the ALU surveyor. The arithmetic logic unit is strictly deterministic. It is 100% verifiable, exact, and executes non-halting logic. If the FPU is our frantic gambler, the ALU is a surveyor out in the field with a precision laser. It performs exact, verifiable arithmetic. 1 + 1 = exactly 2 every single time, universally on every single CPU on Earth. There are no secret seed tables here. None. It operates on a perfect, relentless metronome of clocked voltage. A high voltage is a 1, a low voltage is a 0. No guessing, just absolute hardware facts. Section 4. The DVR wash cycle. So, how do we force our messy, probabilistic AI to actually follow those exact ALU rules? The sources outline a totally ingenious framework called LLM42, which uses a 3-step protocol called decode, verify, rollback, or DVR for short. Step 1 is decode.
The AI uses the FPU to rapidly generate candidate tokens as a very fast guess. Step 2 is verify. A completely separate mechanism takes those guesses and locks in exact mathematical parameters using a fixed shape reduction schedule. And step 3 is rollback. If the fast guess doesn't perfectly match the exact verification due to floating point drift, it forcefully rejects the bad tokens and recomputes everything from the last mathematically sound state. Now, what's really fascinating is that this creates a continuous wash and repeat loop. By constantly running this decode, verify, rollback cycle, the system is actively cleansing that microscopic gunk out of the FPU. It catches the mathematical drift before it can ever corrupt the final output. This whole process effectively turns a wildly unpredictable probabilistic GPU environment into an undeniable forensic silicon witness. It's brilliant.
Section 5. Scaffolding versus permanent agents.
Bringing all these microscopic hardware realities back up to human intent, you start to see a really deep divide in modern computing. On one side, you have probabilistic AI. It's fluid, associative, and absolutely brilliant at exploring multiple reasoning paths. But ultimately, it is just temporary, soft-thinking scaffolding. It's a stepping stone. On the other side, you have the deterministic agent. This is the rigid, permanently hardened, non-halting execution running on the exact ALU. It doesn't guess. It does exactly what it is told, establishing an undeniable anchor in our digital reality. To cross this huge divide, we build what the sources call the semiotic bridge. Think of it like tempering crystals. We have to take the fuzzy, flowing heat of human imagination and AI probability and carefully harden it into rigid, discrete physical logic. And we do this using strictly formatted, deterministic text, things like JSON or code. Text is quite literally the only safe way we have to compile our associative human desires into the cold electrical behavior of a silicon processor. We are, quite literally, tricking rocks into thinking with lightning and text. How wild is that? So the absolutely crucial point here is summarized perfectly in this quote from the architecture documentation. The human pilot applies the intent, but the agent cell executes the sweat. We must maintain this airtight partnership. The human acts as the sovereign pilot, writing the deterministic rules and intent. The machine, stripped of all its probabilistic guessing, acts as the unyielding physical engine that executes that intent flawlessly in the real world. We've journeyed all the way from the chaotic guesswork of the FPU gambler down to the absolute mathematical truth of the ALU surveyor. We've seen exactly how strict text and wash and repeat cycles harden our fuzzy ideas into actual physical reality. But as AI interfaces become more fluid and we rely more and more heavily on the probabilistic machine to do our thinking for us, I want to leave you with this final provocative thought. If we abandon the semiotic bridge, if we stop actively writing the deterministic text ourselves, who controls the physics? Thank you so much for joining me for this explainer. Keep wondering, keep learning, and I'll catch you next time.